First of all, thanks for coming to this session in which we'll discuss Java running into containers. Before we do so, some logistics. So my name is David Delabassee. You can find me on Twitter at Delabassee. I work at Oracle in the Java platform group. I live in Belgium, but just at the France border, and hence my French accent. This is a standard safe harbor disclaimer slide from Oracle, so please read it with great attention. Thank you. Today, well, I'm using a MacBook Pro. And if, like me, are using one of those laptops, you might know that there are some issues with the keyboard. It has been fixed many times. I think that's the fourth time Apple is fixing that issue. They fixed it last time, that was in May. And it's the first keyboard in history to launch with a replacement program on day one. So today I'm going to do a few demos. If any of my demos fail, it's not my fault. It's just because of the broken keyboard I'm using. So, just by show of hand, who is using containers? Yeah, that's what I guess. So I will not spend too much time on explaining what containers are. Basically, containers is a standard mechanism that we can use to package software and its dependencies. There are many runtimes, Docker, Cryo, and so on. Nevertheless, what I will discuss today basically apply to to most of those runtimes. But clearly today, Docker is the most widely used one, and Cryo tends also to get more and more attractions. Containers should not be confused with VMs. So with a container, you have some kind of isolation that is basically provided by using technologies such as namespace, C groups, and so on. But at the end of the day, when you are using a container, you are relying on the host operating system. So basically, the operating system you have in your containers is the same that you have on your host. On the other hand, we have VMs, which rely on a hypervisor to provide a stronger isolation. That means that you can, for example, use different operating systems within the guest than we have on the host. You can have containers within a VM, but not the other way around. And to make things easier, we have in between kata containers, which basically try to solve one of the issues we have with VMs. So VMs provide a very strong isolation, but they are expensive. Starting a VM takes quite a bit of time. Kata containers are basically trying to solve that. So providing strong isolation with the benefit that we have. So basically merging the benefit of containers and VMs. Sorry. This is a survey that was conducted by Stack Overflow a few months ago. And basically, it shows that 46% of the people who took the time to answer the survey are not using containers. That basically means that more than half of the people that filled the survey are using containers. And I think that containers those days is a given. It's hard to work without containers. How can we explain that? Well, the cloud. I mean, the cloud landscape make containers very obvious. So if you look just at Java, there are many tools that we can use and tools that basically makes containers very easy to use. You can create containers directly from Maven using different plugins. There are different microservices frameworks, such as Helidon, Quarkus, Micronaut, and a few others, that provide container support out of the box. So when you build your artifact, you build a jar, you can directly specify, okay, I want that jar to be turned into a container image. So that's very transparent. And then on the right side, we have the FaaS space, the function as a services space, the serverless space. If you look, there are different solutions. And if you look in that space, all those solutions, so all the FaaS solutions are basically using container, either explicitly or implicitly. So sometimes you know that you are using containers because containers are exposed. So to write a function, basically, that function is wrapped into a container. Sometimes you don't know that containers are used. But still, if you have the ability to pick under the hood, containers are used. So basically, what I'm going to discuss today apply to the frameworks, but also to the FaaS, the serverless space. So Java in containers, JVM in containers, towards a perfect symbiosis. So what do we want to get when the JVM runs within the containers? Two things. First, the Java virtual machine needs to behave correctly when it runs within the containers. And we'll see that it was not always the case. In the past, we had some issues regarding that. And then something that we need to focus on is what we call the latency. Historically, Java has been designed and tuned basically for long-running application. So if you have an application that takes like a few seconds to start, it doesn't really matter, because at the end of the day, that application was going to run for days, weeks, months. So the startup cost doesn't really matter in such a scenario. With containers, the dynamics is a bit different, because containers comes and go. You can start containers very quickly, so that basically means that you might start a lot of containers. So if you are doing that, obviously the startup time is something which is very important. This is even more important if you are using Java within the serverless space, because when you have a function that you invoke, the function will only live for 1 second, 2 seconds at most. So obviously you don't want to pay a huge startup time penalty when you have such a short lifespan. So the behavior within containers, and then the latency. That's what we're going to discuss now. So first, I will start with a very simple Hello World demo of a containers. So let's see. I have a very basic Docker file. So I take a Java image. I create a directory. I have a Hello World application that I copy in my containers. I compile it, and I run it. The application in itself is pretty basic. It's simple. It's simply a Hello World that just displays some information about the environments, like the number of CPU, the memory available. Am I running within containers or not? Those kind of things. So that's pretty basic. So Docker build -t, let's call that JAX. Everything was pre-cached because I had some issue with the network, so I built it before just to make sure. So let's run that containers. So that's basically my Hello World application, so it's pretty basic. I'm using a quite old version of Java. The vendor is Oracle, and so I have three cores, and so on and so on. So let's have a look at that image very quickly. So the image is JAX, and that image weighs 600 and over 600 megabytes for a simple Hello World. So that's already an issue. And that means that to run a very basic application, we have to carry basically more than 600 megabytes. And clearly, that doesn't really fly well within the container space. So that's something that we will look at. How can we solve that? That's one of the things that we will discuss. So I will come back to that simple Hello World later on. So let's first talk about the latency. If you have an image that weighs 600 megabytes, that means that each time you need to start up your containers, basically the containers will have to be loaded from the registry. Obviously, the larger the image is, the more time it will take. Even though we have very high bandwidth and so on, you don't want to have to load from a registry 600 megabytes just to show a Hello World. So if we break down the latency of containers, there are basically two levels. The first one is the time the containers take to start up. And that's not specifically tied to Java. So you might have the same constraint and the same issue regardless of the programming language you are using. Once the container is started, there's the Java stack layer, the Java stack layers. So basically, we need to start up the JVM, and the JVM needs to start up our application. So that's basically the two levels we can try to work on, the container level and the Java level. So if we look at the container level, we have to keep in mind that basically a container is basically made of different layers that are stacked together, and that basically will form our container image. At the lowest level, we have the operating system layer. Then on top of that, we have what I call the Java runtime layer, and on top of that, we have our application, so our Java code and possibly some dependency that are needed by our Java application. And the main goal is really to try to reduce as much as we can those layers. That's one way of basically reducing the startup time and also improving the density of our containers. We want to reduce those layers size as much as we can. So if we go top to bottom, so at the Java application layer, from a JVM standpoint, there's not much that we can do. We can give you some advice, like, for example, watch out about the dependency that you are using, watch out about the transitive dependency, make sure that you don't have any dependency in your application that is not needed, those kind of recommendations. But it's more some best practices that we can give and nothing else. If you have stuff that are relatively static, well, it might be a good idea to put them in the different layers. Basically, we can leverage more the cache mechanism of the containers, those kind of things. And then there's something that we can use, that's CDS. That's something that we will discuss later on. Moving down, so we have the Java application layer, then we have the Java runtime layer. So there we can clearly do quite good things. We can use jlink. So jlink has been introduced with Java 9. And jlinks basically give us the ability to create a custom runtime for our image. So the idea is that we have our application, and jlink will basically create a runtime that only carry the modules that are needed for that application to run. Just those modules and nothing more. So to give you some idea of the benefit that we can expect from jlink, I took a serverless Java function running in FN with OpenJDK 13. So a whole JDK weight 300 and let's say 20 megabytes. So that's quite heavy. That's a whole JDK. The next thing that we can do is basically take a GRE. The issue is that today we don't have this notion of GRE anymore that we had in the past with, until Java 8. What we can do, we can create our custom runtime image using jlink. Here I did something very stupid. I created a runtime image with all the modules. And clearly, I don't think there is any way of creating an application that uses all the modules. But this is, again, just to show some idea of the weight. So a runtime image that carries all the modules of the Java platform, 168 megabytes. So we already see that by switching from a whole JDK to a runtime image, well, we already save a lot. Not only that, it's also a good practices in the container space to basically reduce the surface. So basically the idea is that we want to have in our containers only bits that will be needed to run our stuff. And clearly, to run an application, a Java application, there are stuff in the JDK that are clearly not needed. So it's also a good practices to do that. Next, we can use jlink as it was designed for. Create a runtime image that only carry the modules that are needed for our application. In this case, this is a Java function. By doing that, we go from 168 megabytes to 50 megabytes. So that's another huge win. We can remove some information that are not needed using jlink, like header files, man page. We can strip out the Java debug information, those kind of things. By doing that, we'll go from 50 megabytes to 48 megabytes. So that's another win. And then jlink offered two levels of compression, compress 1 and compress 2 being a zip deflate. If we use zip deflate, we go from 44 megabytes to 34 megabytes. That's another way of reducing the size of your layers. Now, keep in mind that if you are using compression, you will have to pay some penalty to decompress the stuff that you have compressed. So maybe it might not be a good idea to use compression in jlink just to try to reduce the layer size. I mean, the benefit that you will get by reducing the layer size might be lost when we need to decompress those layers. So, in a nutshell, a full JDK 316 in this case to 278 for a runtime that carry all the modules, and then we can strip out stuff that are not needed in that custom runtime image. So basically, we can easily go from over 300 megabytes to less than 50 megabytes by using jlink. Now, this is a serverless Java function. So a serverless Java function, in that case, only needed two modules, the base modules and the logging module. So it might be a too optimistic scenario. So what I did next, I basically took an enterprise application, a server application. And I'm sorry for that, but the only one that I quickly found was the Minecraft server. but that's still a server. So the Minecraft server is open source. It needs 12 modules to run. Those 12 modules on JDK 13 weight 88 megabytes. Now this time I've done my table a little bit differently. So if you strip debug, so if you remove the debug information from those 12 modules, you will save 14 megabytes. If you use compress1 on those 12 modules, so from the 88 megabytes, you will save another 28 megabytes. And obviously you can combine, except compress1 and compress2, it's one or the other. Now, if you remove the header files and the man page, you will not save anything because they are not included, at least in the OpenJDK 13 release. That's also something that you need to be aware of. Where are you taking your JDK runtime? I did another exercise, OpenJDK 11 JDK coming, so the Debian distribution basically of the JDK. All modules weight over 500 megabytes versus, well, I don't have the all modules here, but it was all modules here 168 megabytes. And that's an issue that they have on Debian is because they are basically carrying the debug information, the native debug symbols within the libvm shared object. So that's very expensive. If you strip out and only use the modules that are needed for the Minecraft server, you will go from 154 to 469 megabytes. So that's still huge. The good news is that in Java, I think it's Java 13, we have introduced a new capability that gives you the ability to strip out the native symbols from the custom runtime image that jlink produce. So that's something that obviously you're going to use, you want to use if you're using one of those AV distributions. So using jlink is something that we can use at the Java runtime layer. Now let's talk about the operating system layer. Well, we have two choices. Either we are using a standard Linux distribution that is relatively lightweight, or we are using something like Alpine. So Alpine is security-oriented, lightweight Linux distribution that weighs between 4 and 5 megabytes those days. It's basically a full-blown Linux that you can use to run application. Obviously, it doesn't have all the bells and whistles that you will find in typical Debian distribution, but most of the time you don't really need those bells and whistles. But there is one issue with Alpine. Alpine has been compiled for Muscles. But Muscle is basically an alternative to libc. libc being the C++ library that the standard OpenJDK JVM use to talk to the underlying operating system. So OpenJDK is compiled using libc, and Alpine requires Muscles. And we have this project Portola under the OpenJDK project, whose goal is basically to compile OpenJDK on top of Muscles. So that means that with Portola, you can use OpenJDK on top of Alpine, for example. Now, it's not something that those days you want to use in production because, well, it's available in the, I mean, it's not something that we recommend to use in production. It's not yet prime for that, but that's something that you can certainly look at. So I will show you a quick demo on how it works. For that, I'm going to use FN, which is an open source FaaS platform. I had a colleague that had a demo, that has a session. Tom had a session yesterday on that. So FN is an open source container native FaaS platform. The nice thing about FN is that, so it's a serverless platform that gives you the ability to create serverless function in Go, Node, and obviously Java, and so on and so on. And under the hood, containers are being used. So that's why I'm using FN. It's basically a quick way to use containers. So let's have a look. So in FN, everything is in containers. So I have Docker running. So I'm going to start FN. Oops, sorry, that's the keyboard. FN is started in detached mode. So if I'm looking, if I look again in Docker, I have FN running. So the way it works is the following. So FN init, runtime, Java. So I'm going to create a serverless function using the Java runtime, and I'm going to call it JAX. So if we look at the JAX directory, we have a bunch of files. So we have a hello function, which is basically a simple hello world Java function that you can easily extend. we have some GUnit. We have a GUnit class that has been created to basically test that function. We have a pom.xml, so basically a serverless function in FN is simply a Maven project, and so on and so on. So we have bootstrapped the function. Now we want to run the function. So to that, we need to create what we call an app being simply a way of grouping together related functions. So fn create app JAX, and now we can deploy it. So fn deploy, we're going to deploy in the JAX app. The function is JAX, and we're going to use verbose so that we can see what happened behind the scenes, and we're going to use local to save sometimes. And you see that basically behind the scenes, in this case, Docker is being used to compile the function, so to create a jar of the function. Then it's being used to put that jar within an optimized runtime image for our function. So now we can invoke the function. So fn invoke JAX. So I'm invoking the JAX function in the JAX application, and everything is taken care of by the fn infrastructure. So obviously here I'm just invoking the CLI, but I could invoke the function through HTTP, or I could define additional triggers. And the only thing that really matters from a programmer standpoint, I just create Java functions, so I don't have to deal with the underlying Docker container stuff. So now, fn init, runtime, init, JDK. So you might know that JDK 14 has been released 2 weeks ago, so I'm going to use JDK 13 has been released 2 weeks ago, so I'm going to use 14, and I'm going to call that function JAX 14, and it's not runtime, it's, sorry for that, that's the keyboard. Runtime init image. Okay, I have a new function, so let's deploy it. Fn deploy app JAX 14, I think. -v. So again, the function is being built and so on, and it's deployed. So let's invoke that function, and there's nothing really fancy in that function. So hello, and then I have the ability to pass it to some payload like -JAX. So hello JAX, and then here you see this 14 early access plus 2. That's basically the runtime version. So it's basically a JDK 14 that I'm using. Nothing really important here, but you see that here we have the image of, so the container image of our serverless function that has been created by fn. So let's dive into that one and see what we have there. So I'm using dive to see what we have in the containers. So we have first a 4.1 megabyte layers. That's the operating system layer. So it's a Linux that is capable enough to run Java application. We then have a 2.4 megabyte layer. We see it on the right. That's the function layer. So we basically have this function jar that weighs 3 kilobytes. That's the function itself. And then a bunch of dependencies that are needed by the Java function. So that takes a little bit more than 2 megabytes. And then we have this 34 megabyte layer. That's basically the Java runtime that is needed to run the layer. It has been created by jlink. Sorry. So that's a runtime with all the modules and just the modules needed to run our Java code in this case. And finally, we have this 20 kilobyte. That's just a share object that is needed by fn. So if you peek under the hood, you can, let's see, JAX 14, I think, yes, more. If you look at the Docker file that fn has created, you should see somewhere, yes, that, well, jlink is being used, level compressed 2, no header files. This is useless in this case. That won't give us any benefits, and so on. So basically, jlink is used. Not only that, had modules, and then we are using JDEPs, which is another tools of the JDK that gives you all the modules required by the jar that is being passed a little bit further down the line. So basically, you see that by using jlink, in this case with fn, with Alpine, we can greatly reduce the layer size of our containers. That's something that we can easily do. Now, let's talk about the second level, that is the application startup time. So we know that we can do a few things at the container level to reduce the latency, so to improve the startup time of the container. Now let's have a look at what we can do on the Java side. This is a startup time from Java 8 to 9. And clearly, smaller is better. So in 9, we had a big regression in terms of startup time. That was not really something that we can be proud of, but the thing is that in 9, we had a lot of stuff. So that's something we had to live with. Now, I'm going to share a secret that we use internally at Oracle that we're using to basically reduce the startup time of our Java application. And basically, we just use the latest and greatest version of Java. But don't tell anybody about that. So you see the startup time that we have in 13 those days is below the startup time that we had in 8. Not only that, in 13, we obviously have more capability that, as a developer, we can leverage from the platform, like HTTP2 support, modularity, TLS 1.3, and so on and so on. But a bunch of new capabilities that are provided in the platform. So overall, that startup time is something that we're looking at in each releases. So if that's something that really matters to you, well, try to have a look at the new releases of Java to make sure that you can benefit from those improvements that we're doing within the platforms. And startup time is just really one aspect, but that's one important aspect. So something else that we can use and that we should use is CDS. Anybody is using CDS today? No? Anybody knows what CDS is? Okay, few hands. That's good because CDS is clearly not something new. CDS has been in the platform since Java SC5. So the idea with CDS, class data sharing, is very simple. So each time you start an application, basically the JVM will have to look at the class on the disk and turn that into an in-memory representation. So basically it will have to parse the class file using the class file format, those files, to basically turn that into an in-memory representation of the bytecode that we have in those classes. And that's a very expensive operation. Not only that, obviously, we have more than one class. We have the runtime classes, and we have all the classes of the application. So each time the application needs to start, that expensive process needs to be done. The idea with CDS is pretty simple. We do that expensive process once. Once we have the in-memory representation of the classes, we just dump that into disk. And the next time the application is started again, well, we do an in-memory mapping from the disk directly into memory. So we don't have to do all those expensive operations again and again. Not only that, that will reduce the startup time, but that will also improve the memory footprint. And that's also very useful if you have multiple JVMs, because basically, given that in-memory information is read-only, it can be shared between multiple instances of the JVM. So that's really something that you should leverage. So let's have a quick look at CDS to see what benefit we can get from CDS. So for that, I'm going to switch and use an Ubuntu box in Oracle Cloud, just because I need to use. So I have this perf42 alias, which is basically just a way of invoking perf42 time. So let's see, Java version, Java 13. I have this Hello World application. So let's compile this guy. Let's invoke it. Okay. So what I'm going to do next, I'm going to invoke that very stupid application 42 times, and without CDS and with CDS, so that we can see basically what benefit we can, to observe the benefit of CDS. So for that, I'm going to perf 42, and I'm going to dissolve the first time CDS, because those days CDS is enabled by default. So let's invoke that guy 42 times. So on average, 196 milliseconds without CDS. Now let's do it again, but this time with CDS. So let's just get rid of that flag. I could have said Xshare on, but that's the default well, it's auto, I think, the default value. So 196, I think, versus 131. So 131, 196. So basically, with CDS, the startup time with CDS is only 66% of the startup time without CDS. So that's clearly something that is beneficial. Now, it's not something new. It has been in the platform since Java 5, but it has been improved through the years. So at the beginning, CDS was limited to the runtime classes, and it was limited to the serial GC. That limitation has been lifted, so it supported multiple GC in Java 9, and also application CDS. So it can be used with custom class loader to basically do a dump of your application classes. Back then, it was a commercial feature. It has been open source in Java 10. So in Java 10, you have the full-blown application CDS capability that we had in 9. And we're keeping improving CDS in 12 and 13. In 13, what we do is the following. So to do the dump of the classes of your own code, of your own application, basically it was a three-step process. So first, you need to create a list of the classes that you want to dump. Then you need to dump those classes. And finally, you use that dump to run your code. In 13, it's easier. You just start the application 1 with that archive class at exit flags, and the dump will be automatically created for you. The next time you start your application with, and you specify where we can find that archive, and there you go. You have the benefit of CDS and app CDS directly. Now, I told you, and I show you a very good example of CDS through the demo, but that was a very basic example. So obviously, the benefits were very obvious. So don't take my word for it. This is a tweet from Charles Nutter, the JRuby project lead, I think 2 weeks ago, where basically he was praising CDS from Java 13. This is the numbers that he published. And well, just look, for example, at the bottom. So JRuby without CDS on 853 milliseconds. JRuby on 13 with CDS and app CDS, 717 milliseconds. So that's, I mean, when we're in those range, shaving more than 100 milliseconds is a huge win. So we've talked about CDS. We've talked about jlink, but we can go further than that. You might have seen a session from my colleagues yesterday about Graal VM. So Graal VM is an open source high-performance polyglot virtual machine. It provides many capabilities. I'm just going to quickly discuss about one, that is the native image capabilities of Graal VM. So the native image capabilities basically give you the ability to take a Java application and ahead of time compile it into a native executable. The benefit is that that executable will not need any external dependency like a virtual machine to run, for example. Now, we're starting from Java code. So your code, for example, expect to have some memory management capabilities provided, like some GC capabilities provided by a VM. So what Graal VM, and more specifically native image capability do, it embeds directly into that native executable a virtual machine that is called SubstrateVM that will provide those basic capabilities that are typically provided by a Java virtual machine. The benefit of using native image capabilities is twofold. It will reduce the image size, and it will improve the footprint. And I forgot one, it will also greatly reduce the startup time of the code, and that's clearly the most important one. So the reduced image size is more a side effect benefit, but given the startup time benefit that we have, that one is less important. Now, that doesn't really come for free. There are today limitations with Graal VM. Today, Graal VM only supports Java 8. The next release will support Java 11, finally. There are also some other limitations, like, for example, if you are using, reflection, for example. Well, it might be difficult to use Graal VM in those cases. So, I mean, Graal VM is great. If you can work around those limitations, have a look at Graal VM. It's really something that will provide great benefits within the serverless space. Sorry, within the container space. Now, something that you need to keep in mind is that, for example, today the GC capability that we have in SubstrateVM, enhancing the native image capabilities, is not on par with the GCs that we have in Hotspot. So there's no way we can beat with Hotspot the startup time of Graal VM. But for long-running application, you should do the math and have a look at which one provides the most benefit over time. Just to give you some idea of Graal VM. So this is again, so FNLS. So I have here a Graal application with one stupid function, FNLS. So it's a Java function. If I invoke Graal native, it's again a hello world function, hello BCN, doesn't really matter. But if we look at the image, so this is the image of the function. It's a Java function that has been AOT compiled into a native executable. So 4.4, that's the operating system layer. And then we have this 16 megabyte. And that's basically the function with SubstrateVM, nothing else. It's all it takes to run our Java function. It's that simple executable that embeds our native compiled Java code and everything needed to run it. And given that we're using FN in this case, we still have this 20 kilobyte shared object needed by the platform itself. So it has nothing to do with Graal. So that's the type of benefit that you can get. So this will greatly reduce the size because there's no external runtime needed. And the startup time of that executable is blazing fast. Okay, final point. JVM should behave as good container citizen. I'm not going to go into details about those because basically it's a very busy slide. But the idea here is that I just wanted to highlight some of the things that we're doing from release to release that are basically addressing the JVM running into containers. So you can see that we've done stuff in 8, in 10, in 11, and we still have a few tickets open. So everything is not yet done. But from release to release, we are actually investing to make sure that the JVM works nicely when it runs into containers. And why this is important? Well, ergonomics is, it's important that Java behaves correctly in containers because of the ergonomics, the JVM ergonomics. So the JVM ergonomics is something that has been introduced, I think, in 8. And the idea was that when you start a Java application, the JVM will look basically at the environment to try to define some default behavior that makes sense in terms of performance. So it will look at the number of CPUs, the memory that is available, and basically from those basic metrics, it will configure the GC, the heap size, and which compiler to use. So that by default, if you don't do any tuning, you will get a good performance. So that's basically the idea behind ergonomics. And let's have a look at why it's important to be aware that we're running in containers, especially when the ergonomics kicks in. So let's see. So we have this Docker run, it was JAX. So that's the Hello World application that we built at the beginning. So you see that I'm using a quite old Java version. It says that I have some memory, I have 3 CPUs, and the common function pool worker thread are configured based on the CPU. So I have 3 CPUs, so I have 2 worker threads. That's the ergonomics. Now what I can do, I can, if I get the argument right, I can specify that, for example, my container has only access to 2 CPU, 2 cores. And guess what? We still have 3 cores within the containers, and the common function pool is still configured with 2 worker threads. I can say that I only have 1 CPU, and guess what? So that basically means that our JVM running in that container has no clue where it runs. And that clearly means that it will very quickly get killed by the container runtime. It's worse than that. So, sorry. So, one CPU, 64 megabytes, but still, I have three CPU and 44 megabytes. So my heap is clearly not sized correctly. So I can be sure that I will very quickly have a very strong, very severe issue. How can we fix that? Well, in this case, this is pretty simple. So that's typically something that you can only do when you're on stage. Never use the Java latest image. That's a pretty old image that is not maintained. So, OpenJDK latest, that's the official OpenJDK build. It's 13 those days. So let's build that one. So this time, the only thing that is changing is the base image that we are using. And you see, Java 13, we only have one CPU, so the command for join will be configured to 1. And you see that the runtime memory, 30 megabytes. We only have in total 64 megabytes. So you see that it's important for the JVM to understand that it works within containers, because we have the ergonomics that will basically try to do their best to make sure that everything works nicely. And clearly, if the JVM has no clue about where it runs, that's not going to fly for a long time. So, wrap up. JVM in containers, Symbiosis. So we've discussed today about what we can do to reduce latencies, two-level, container startup time, and then the Java application startup time. There are things that you need to do as a developers, and there are things that you can leverage from the Java virtual machine and basically from Java at large. Next, we've talked about why it's important that the JVM behaves correctly when it runs in containers. We have looked at the ergonomics. So, as a conclusion, try to always use the latest Java version and never java.latest. That's not something you want to do. If you can't do that, use the latest Java version, at least rely on an actively supported Java version. We don't have this notion of Java runtime anymore, but what we can do, we can create our own Java runtime image. You use it. You see that by doing that, not only it's a good practice to reduce the surface of our containers, but it also saves and reduces the size of our containers. Try to move the startup cost at build phases. Typically, Graal, building a native image is expensive. So that's something that you will do during the build. And then it's container as usual. So it's all the good practices that you should follow, regardless of which language you are using, that also apply for Java. So I will just conclude with that. Choose your base image wisely. This is a tweet from a few months ago. The top 10 most popular Docker containers image contain at least 30 vulnerabilities. Java is not in there. But that doesn't mean that we are immune on the Java side. That's something that has popped in May. Basically, it has been discovered that the Debian distribution had an OpenJDK build, which was tagged as released before OpenJDK, I can't remember which version, which was 11, before it was even released. Because, everything is open source, so it's pretty easy. You just build the source, you tag it as released, and, it's not really how it works. So the OpenJDK build in Debian had several had issue because it was not a released version, despite the fact that it was advertised as released. Not only that, the Docker image, the OpenJDK at that time, Docker image was pulling that as the OpenJDK build. So choose your base image wisely, and regardless of where you are taking your base image, secure your base image. That's something which obviously is important. One last time. Okay, it's secure. Slow-mo. Now it's really secure. And with that, I'd like to thank you for your time.